Hello everyone. This is a video lecture for Calculus 1, Section 2.5, Continuity. So I'm just going to talk about what continuity is, what does it mean to be continuous, and then discontinuities as well. So continuous is basically just moving along, and there you go. That's a continuous function. Here's something else that's continuous. Okay, so these are continuous. Continuous. What does it mean to be continuous? Well, you didn't really get to see me with my hand, but I never had my my pencil leave the paper. I never had my pencil leave the paper. So the pencil never leaves the paper. You know, kind of like an Etch-a-Sketch, and it's always on. It's just where is it at the current moment. That would be continuous here, okay? These are normal functions. I'm just going to make up some. Here we got e to the x, we got x squared, we got all of them. So many different functions are like this. Not all of them, obviously. Okay, so we got a lot of continuous functions. That's cool. So what does it mean to be not continuous? What would be a discontinuity? And so here's an example. I can come along, and then I got a circle, and then it keeps going. The circle itself is not necessarily the point of which I'm talking about continuous. It's just the fact that there's another point somewhere else. And so this right here, having this... well, I'm just going to call it, it's a removable discontinuity. Removable discontinuity. Notice that it was continuous except for this one point. Okay, this one point. And then we have another kind that could do something kind of like this here. And so this is called a jump discontinuity. Discontinuity. These terms are important. I'm telling you if they weren't important. Obviously, because it jumps to a whole new place and then it keeps going. So these are the different styles of discontinuous functions, I guess you could say. Let's do some homework problems. So 25008. It says a jump at 7, like as in x equals 7. And then it says a removable discontinuity at x equals 5. And so what does that look like? And I'm not sure how this problem is exactly, if it's just a multiple choice or something. I cannot remember. But it looks probably something like this here. There you go. So this would be here at 5. This would be here at 7. Okay, well, there you go. Ta-da! I don't know. Next one, 25012. So it says find the discontinuities. So find the discontinuities. That's good enough. And so I've got f of x is equal to 6 over 1 plus e to the 1 over x. So how do we find that? Well, removable discontinuities are, in particular, when the bottom equals 0 or something like that. You can relate them to vertical asymptotes. Those are going to be, generally, they could be, well, they're discontinuities. It kind of depends then, because they do jump also in a way. Moving on. So to find the discontinuities here, in this particular case, I'm going to say find when the bottom is equal to 0. So I'm going to take the bottom off to the side and set it equal to 0. Let's move the 1 over. And let's pause for a second. I'm saying that e to the something is equal to a negative 1. And this is e to the x. And so I know that it's e to the 1 over x, but like this right here, this component is just a number, right? So I'm saying we have a number, so it's e to a number. And e to a number is always up here. Is it ever going to be down here at negative 1? No, never. The graph just doesn't do that. So I'm going to write never. And so that I guess it would be no discontinuities, right? Because we tried to do the bottom equals 0 thing. That doesn't happen, so we're done there, right? Well, kinda. Yes, that bottom did not work. Bottom equals 0. We tried this bottom and it didn't work. But what about this guy? What about, in particular, this bottom right there? You see, every bottom, every division we should be looking at. And so here in this particular case for this one, I'm saying again, bottom equals 0 for the division stuff, and I got x equals 0. That would make it blow up. That would be some kind of problem. And so this is my discontinuity at this particular place. And, well, that was it. There's not really a lot else to do. Now, I think they're going to want to know what does the graph look like, and I'm just going to graph it for you. It looks something like this here. There you go. So there's your graph. As far as what's going on here, I think it's probably two open circles and not a solid. So it looks like a jump discontinuity. There you go. All right. Cool. Now the next few are like super easy. And I think they're just putting this in here to kind of talk about continuity in general with limits and stuff. I don't know. So if you remember our limits from last time, what we're going to try to do, the ultimate goal is to plug it in. And I'm going to tell you, that's exactly what we're going to do. So this function here, is this continuous? Is this function continuous? And the answer is sometimes. It's continuous as long as it's within some kind of domain or something. I believe it's going to be -5 to 5 is kind of like its domain. And so anything from -5 to 5 should be fine, pretty much. I don't know. And notice that it is including this. So there's my 5. I'm going to plug it in. Is it 5? Maybe it's something else. Maybe it's something... or it's around 5, 5.1 or something like that. I can't really remember. The point is that it's around this area that it should be fine, and 5 itself is going to be okay. Watch. So I have the limit, and ultimately what I want to try to do is plug it in. So I'm going to plug in a 5. Now, if something like blows up or something, that's fine. We can talk about it, but I mean, I don't see any problem just trying to plug it in. So we got 25, 29 minus 25 is going to be a 4 in there. So we get a 10, and, well, that's your answer. They just said find the limit. We plugged it in, and we're done. So what does this have to do with continuity and stuff? Well, it's just that this function is continuous within our limit area that we're trying to find. I don't know. I think that's good enough. The limit is x goes to pi of 6 times sine of x plus sine of x. Now, I know it's kind of a nested sign, and that is really weird. This does not make a lot of mental sense, personally. But my domain should be negative infinity to positive infinity. It's not going to be uncontinuous anywhere, discontinuous. So plug it in directly, and let's just see what we get. Again, I'm just going to remind you, my kind of like go-to for limits is basically we're going to plug it in. Now, sometimes, again, will it blow up, and then I have to try something else? Right, yeah, of course. But, you know, ultimately we will be plugging in a number eventually. Okay, so sine of pi, that's going to be a 0. And notice here that we got now sine of pi. So, well, we get a 0. And yes, the answer is 0. So there, I guess. You can see they're very simple. They're not hard here. Why are they including them necessarily? I don't know. So we got a piecewise function. And I don't like piecewise functions. I don't. They're just kind of like not my favorite thing ever. But we're going to have to do it because guess what? It's on the homework. So... you can see that I'm not like trying to skip out on problems that I don't want to do. I want to do this work with you. I want to do the easy ones and the hard ones, kind of a mix. And so yeah, I'm going to do the piecewise also, which I really don't like doing, but it's okay. So piecewise, just as a reminder of what's going on, these are like mini domains, and so we have three separate functions all put together, and we just mush them into one graph and call it a day. So as long as I'm negative, x is negative, it's going to look like this. And the graph for that goes up to 6. 1, 2, 3, 4, 5, 6, and it's a line 45 degrees, basically. Now, notice that it does not have an equal sign there, and so this is going to be an open circle. Okay, so keep that in mind. Let's keep going. The next one is e to the x. Well, e to the x starts here at 1, and it does equal. See how it has the equal sign right there? So it's solid this time. And it's not going to go very far. It's going to go to, like, x equals 1. So, I don't know, right around there. Again, that's x equals 1 right there. Not to scale, but it's close enough. And again, that's an equal, so it's solid, and there we go. And then the last one is this 2 minus x as long as it's more than 1. Where it actually ends up starting is right below that, and then it kind of does this. Again, that's going to be a -1 slope, so a -45 degrees. Again, not perfect to scale there. So this is the graph. This is what we're looking at here, and now they're going to ask, where are the discontinuities? And there's going to be two of them, if you can just, well, see them right there. We have, first off, a jump discontinuity here at 0. And we have another jump discontinuity at 1. Ta-da! We answered them. I think that the problem has a little bit more, I guess, that we have to do. I'm not exactly sure. On the side here, I wrote continuous from the left. And here for this guy, I wrote continuous from the right. Okay. So why did I write that? What does that mean? And I'm pretty sure it's part of the answer, otherwise I wouldn't have done it. Continuous from the left and right. So if we're looking right here at x equals 0, which is going to be that guy right there, notice that we have a lot of graph here on the left side, yeah? And so that's good. But is there anything right here next to this point, I guess you can say, anything next to this on the right side? Nope. Because what happened is that it jumped. It's like a whole new place, a whole new graph, a whole new location. And it's also right here. It's continuous, I guess you could say, on this side. But I'm guessing what they're trying to get at is it's, I don't know. I'm not exactly sure what they're getting at. But that's what I wrote, and that's what they want. So, well, there you go. Continuous from the left. And this guy right here, same thing. It's going to be continuous from the right side. There might have been a little bit more information here that I just didn't write down. Moving on. So, I mean, it's not that hard. It's just, sometimes it's confusing. Okay. So, there's another piecewise function here, but this one's a whole different kind of problem. So, I got c, little c, x cubed plus 6x. And they say that x is less than 3. And then I have the next one is x cubed minus cx. And this is when x is greater than or equal to 3. And they say find c so that it is continuous. Find c so that it's a continuous function. A continuous piecewise function. I don't know what this will look like. But the idea is that I have like some kind of piecewise thing going on here, and then it does its own thing over here. It's like a sharp break, but they're literally on top of one another. It's not looking kind of like this here, like on a previous problem. We're not looking for jumps. We want it to be continuous, even if it's a sharp little corner. That's okay. So what value of c would make that happen? And what we have in common with these two is the x equals 3. X equals 3 is kind of like our highlighted point right here. It's going to be 3, and I'm work at 3. Okay, so that's the goal here. So I'm going to plug in a 3 for x everywhere and see what happens. Now remember, that's a cube because a square is not correct. So that's when I plug in 3 there. And I'm going to set it equal to whenever I plug in 3 to the other side. And the reason why I'm setting them equal to one another is because that height, the y value right there, they're the same. They're the same y value. They're the same point at 3. And I don't know what that y value is going to be. I don't really care, but they better be the same. So 3 cubed is 27. So I got 27c. And then 6 times 3 is 18. Here again, I got a 27. And then here we got a 3c. If I add 3 to the other side and I minus the 18 over here, I should get a 30c is equal to, doing the math here, 9? No. Why did I have a 12? Oh, I messed up the problem. Okay. I mean, this is still okay. I mean, everything I'm doing. Let's just finish this one off, and I'll show you what I did wrong. It's fine. So 27 minus 18, I think that's a 9. Let me just verify with calculator. Yeah. Okay. And so then I divide by the 30 on both sides. So 9 over 30 will reduce, just if you want it to, it's 3/10. And there we go. All right, and then we're done with this problem. Cool. Now, where did I mess up? Well, I was copying my notes, I guess, a little too fast, and I said it's not a square. Well, it is a square right here. Okay. Oops. So your homework will probably have a 2 there. I don't think that number will randomize. And so it's probably a 2. And so let me just redo it in blue for the 2. So this right here would be a 2. But that right over there is still a 3. There's a 3 right there. And so what we're going to have instead of this is going to be a 9. Everything else is the same. So when I add the 3 over to this, I don't get a 30. I get a 12. And again, I'm going to divide by the 12 on both sides. And so then what I get here is not 3/10, but you could see 9 over 12 makes 3/4. Okay. And that's what I have on my notes. So I'm glad that we talked about it. You can see that the process is all the same. The ultimate idea is that you plug a 3 in and solve for C. Okay. One last problem. Yep, that's it. This is a very short section. So it says for what x values are continuous? What x values are continuous? And I want to note, I just want to tell you that before I even show you anything else, if they're asking for what x values are continuous, you're not going to be putting in a 0, 1, 2, blah, 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 because that inherently is not continuous. Continuous is a flow of numbers. And so you would have to put interval notation in some way, something like negative infinity to 0 or something. That's what they're actually looking for in this case, okay? So let's actually look at the function here. It's another piecewise. We got 0, just 0, if x is rational. And then we got 6 if x is irrational. Okay. What do they mean? Well, rational means ratio, means a fraction. But that doesn't necessarily mean that this guy won't have fractions. It's just a little different. Let's talk about rational functions for a second, okay? That would be like 1/2, 3/4, I don't know, 5, because it's 5 over 1, -7. These are all rational. Irrational would be something like square root 2, square root 3, that kind of stuff. Now, they're not including e, that's another one. E, pi, there you go, there's another one. They're not including i's. We're not talking about imaginary numbers and stuff like that. We're just talking about real, honest numbers that are not fractional, I guess you can say. You can't like put them into a fraction. They're like no repeated decimal digits, that kind of stuff. Okay, so there are an infinite amount of these guys, and there's an infinite amount of these guys, and what the graph would look like, and this is very silly, it would look basically like this here, and they're just like they're just dots all over the place. If you actually were able to graph this and say, like a graphing calculator or Desmos, which I don't know how you would do it, it would just it would just be almost like a solid bar, because it just keeps going up and down so much, because there's no continuity. It's always right here at 6, and it's always right there at 0, but then you can't be both, and it's just all over the place. In a way here, This is not continuous at never. So I'm going to say never continuous. And so I think you type none or something in the box. I have none. That's my answer. That's it. That was it. So I know it's weird, but I wanted to talk about it because it was weird. I don't want to leave you hanging. All right. That's all I got for that section. So thank you very much and have a great day.